Hey everyone, it's Miss Pasega, and today I'm going to guide you through a quick lab and then you are done. So I promise I will shut up in a minute. I just want to show you how to do this. This is going to be like the lab practical from the midterm. First, you start off with 3 possible independent variables. In this case, your possible independent variables are the initial number of radioactive nuclei. So you're going to be going into the PhET simulation and trying 10 atoms, or 20 atoms, or 30 atoms. You could try a whole bunch of atoms, but if you try a whole bunch of atoms, you're going to have to count them later. You'll see. So, initial radioactive nuclei, its symbol is N0. That's one independent variable. You're going to go to the second simulation and test half-life. The second simulation is here. You would change the half-life from small to medium to large, and if you need to, you can step one step at a time. That'll read a different number of seconds, so step, 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 so that you have specific numbers of seconds you're studying. Okay? So, we've got one potential independent variable is N0, another is half-life, small, medium, or large. And finally, T is the amount of time, increasing the time it takes radioactive nuclei allowed to decay. So maybe I would measure 30 seconds versus 60 seconds, or something along those lines. Up to you. And we're trying to see how those 3 variables affect how many radioactive nuclei, N, that's the symbol for total radioactive nuclei, are set at a remaining time. So the reason you may not want to start off with 30 is because let's say you measured 20 as your years of time, then you'd have to go count all of the ones on the screen remaining. It's up to you though. So you're going to test the initial number versus the final number. You're going to test the half-life versus the final time. So let's say you did small half-life at 30 seconds, medium half-life at 30 seconds, large half-life at 30 seconds, and counted how many are left over. And finally, time. You'd allow the time in this simulation to run out, and you'd count how many are available at 10, how many at 20, how many at 30, to see which of these 3 variables has an effect. Using the same simulation, I actually want you to take real, actual data. So if you want, you can use that run forward 1 second, so step forward 1 second to take accurate amounts of time. Pick any one half-life value, and at these intervals, figure out how many remaining nuclei there are. Then pick any different half-life variable and measure the same times again. What I want you to do then is go graph both data sets, screenshot, paste it into here, screenshot, paste it into there, and finally, you'll have tested 3 variables. One that you should be able to get from the earlier part of the lab, and time and half-life, which you should get from these 2 graphs. I want you to put them all together and make an equation. The final number of nuclei, N, the final number, how does it depend on the original number of nuclei? So if I have 100 versus 1,000, how would that change the final number? How does the time impact it, and how does the half-life impact it? And keep in mind, we're going to go over all of this on Wednesday. Best of luck. See you soon.